Okay, so this is going to open up our air, atmosphere, and climate change unit. And so this is going to be basics about the atmosphere, basics about weather, and then we'll start getting into the air pollution and the climate change in a later video. So the modern atmosphere, we started quite a long time ago. The original atmosphere surrounded the Earth when it was homogeneous, before it had differentiated, so before it had the layers. It was probably composed primarily of hydrogen and helium, and then a second atmosphere evolved from that with gases from the Earth, and that's what allowed for the formation of the oceans and the formation of life. And then that again evolved into the modern atmosphere that we have today, and that came after we had cyanobacteria that started photosynthesizing. So once you had that oxygen input into the atmosphere, it changed quite a bit and created the modern atmosphere that we have today. So we didn't reach enough oxygen to hit modern levels until about 400 million years ago. So up until then, there was oxygen, but it was slowly increasing. So the Earth's atmosphere is a really thin shell, about 120 kilometers, compared to Earth, which is the size of the Earth, which is on the order of 10 to the 4th kilometers. So the atmosphere is just a thin layer outside of the Earth, or above the Earth. There are layers to the atmosphere, and make sure you guys know these, and make sure you guys are comfortable with these, and what temperature looks like, what's in each one. So the troposphere is the one closest to the surface of the Earth. So that is, I'll go back. Okay, so that's down here, is the troposphere. This is where most, if not all, of the weather happens, and then up a little bit into here. Jetliner planes are flying somewhere around here. So the temperature starts warm, right? The surface of the Earth, temperature is warm, and it gets colder and colder and colder the further up you go. And then the stratosphere is next. Stratosphere is up here, and the temperature is doing the opposite in the stratosphere. It's increasing. The mesosphere, the temperature is decreasing again, and the thermosphere, it's staying relatively the same, perhaps increasing just a little bit. And then the exosphere is outer space. Okay, so the troposphere. Did I skip one? No. Okay. The troposphere is just above Earth, so it goes up to about 5 to 9 miles above Earth. It's the most dense. Temperature gets colder, and then again, like I said, this is where all the weather happens. The stratosphere goes up to 31 miles above Earth, less dense, drier, increasing temperature gradually, but still, pretty cold. And this is where the ozone layer is. So we want ozone up here. Ozone is good up high. So it scatters the ultraviolet radiation, it absorbs it. Most of the air, as we think of air, is located in the troposphere and the stratosphere. Okay, composition of air. Nitrogen mostly, 78%, oxygen 21%, argon 1%, and then a whole bunch of other stuff. Water, ozone, carbon dioxide, etc. is everything else. Okay, so physicists use or reference the environment, research the atmosphere to talk about the physical properties and processes. So, for example, energy exchange is their big thing. The change in the atmospheric gases, a physicist would explore and research. Chemists look at the behavior of the chemicals in it, so the cause and formation of lightning, how that changes substances. And then they get really into the chemistry of the ozone, and from the chemistry of gases that are introduced through industrial processes. Astronomers and space scientists, obviously, they have to pass through it before they get into space, and then meteorologists, climatologists, and geographers are looking at the lower layers to look at the weather, to look at climate conditions, and to look at the effects of climate and weather on humans. So there's a lot of different people that are studying the atmosphere for different reasons. Okay, so just a quick refresher. Hopefully you guys are all familiar with this, but we're getting seasons because the Earth's axis is tilted. So it creates the opposite seasons in the northern and southern hemisphere. So for example, here's your Earth tilted on axis. If the sun is right here, this would be summertime, this would be wintertime, right? So you would see that there, and it's spinning around. So when the Earth is tilted toward the sun, it's always going to be, spinning around every 24 hours, right? That's a day. So it's always the northern hemisphere tilted toward the sun in the summertime, and then when it goes around the other side, and the sun is still here, it's on the other side, the southern hemisphere still tilted like this, the southern hemisphere would be pointed toward the sun. Okay, so ocean currents. Ocean currents are directly related to the there you go. Directly related to the air temperature and directly related to the movement of the winds and the weather and all that kind of stuff. So sea surface temperature influences the air temperature, and so our ocean currents and the movement in our ocean controls our weather to a huge extent. It also influences the evaporation rates, which controls the rainfall. So ocean currents become very important to the overall climate. This is just a quick model. Ocean currents can be tracked, can be monitored, and end up forming big gyres, which is just big circles. Sorry, hang on, let me go back. Okay, so they form big gyres, which is big circles. So if you're looking at this one in the Atlantic, you will see this year-round, all the time. These are pretty constant currents that have been tracked and monitored, and so we know already about the Gulf Stream that goes up along the coast of the North Atlantic and brings warmer water up north, and then you see colder water going back down south. So this drives air temperatures as well. Two types of ocean currents: the surface currents, which forms the surface circulation, that's those big gyres, and so that water makes up about 10% of the water in the ocean, and is in the upper 400 meters, so relatively shallow water. So those are the surface currents. And then the deep water currents are about 90% of the ocean. This is around the ocean basins, and is density driven and gravity driven. So the density difference is based on the temperature and salinity of the ocean. So for those of you that aren't super familiar with the aquatic aspect of this, with the marine aspect of this, density in the ocean drives all kinds of functions and is essentially the bottom of the food chain, because that pulls up that cold, salty water from the ocean floor and essentially brings it to the surface, and so then that provides nutrients to plankton, which is the bottom of the food chain. And so that density-driven difference is really important to overall climate and overall food chains. Okay, so the primary forces to get the water started is the solar heating, is wind, gravity, and then the Coriolis effect. The secondary forces influence where the currents flow, so that would be more minor stuff. Okay, so again, just a more close-up, you can see the surface currents, you see the Gulf Stream, North Atlantic current, Canary current, and then North Equatorial current. And so that's the Atlantic gyre, which is the one that I'm most familiar with. But you see the same gyre happening in the Pacific Ocean and the same happening in the southern oceans, but notice that they go in the opposite direction. So notice that they're going clockwise in the northern hemisphere and counterclockwise in the southern hemisphere, and we'll talk about that in a little bit. Oh, no. Sorry. Okay, let's do this. Alright, so upwelling, this is what I was talking about. So those currents, those deep currents, bring nutrients up along the coast. So the current is moving up, hits the coast, right, or in this case it would be going this way, hits the coast, goes up, and that forces cold, nutrient-rich water up from the ocean floor, which in turn makes the phytoplankton population grow, which in turn makes the zooplankton population grow, which drives the entire food chain. So this Coriolis effect is huge for primary productivity. This is what is driving the entire marine ecosystem all over the world. Very, very important. Coral reefs have a very specific range of tolerance. So they are a great carbon sink for atmospheric carbon dioxide, because they will absorb that and utilize that to make the actual reef structure, because a coral animal creates a skeleton made of calcium carbonate, and that forms the structure of the reef, right? Because they build on that every year and every year. So that carbon sink is very important and is used in coral reefs. Okay, moving back to air temperatures. As the energy reaches the Earth, the equator heats up faster than the poles, right? Because it's closer to the sun. So then that means that the warm air and the warm water at the equator travels toward the poles, and the cold air at the poles travels toward the equator to equalize this out. So it's this constant battle and struggle to balance us, and that's what brings us our weather. So this is just a diagram of that. So you see the energy coming in, heats the equator more, and then it divides up, and so you see warm going away from the equator, cold getting pushed, and that's creating those gyres, right? That's creating those circles, counterclockwise and clockwise, right? So you're, sorry guys. Okay, so you're seeing that circle created by the sun, created by the air temperatures. Oh. Okay. So the Coriolis effect is simply the fact, there's a lot of math in there, and so just the basic concept is that the water movement is different at the surface and with depth, and the fact that it moves clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. So there's a lot more to this concept that is just literally scratching the surface. I just want you to know that it exists, and that this is what's driving the weather patterns and the water currents, which are in turn creating the weather patterns, right? So Coriolis effect is what's driving oceanic current movement. It's based on temperature and the speed that the Earth is spinning. Okay. So winds are also subject to the Coriolis forces, just like the water is. So the solar heating will move the winds, and that creates the prevailing winds. So again, I'm not super stressed about you guys knowing in depth in the Coriolis effect. Know what it is basically, and then know that it controls prevailing currents and prevailing winds. And this shows you the prevailing winds, so you see in which direction stuff is moving. Same as the water. Clockwise in the northern hemisphere, counterclockwise in the southern hemisphere. This is just not working out for me today. Okay. And this is showing it in a different, looking at it from a side view, so you can see that clockwise versus counterclockwise. Okay, so then air pressure is the weight of the air pressing on the earth, the ocean, the air below it. The pressure depends on the amount of air above it, and decreases the higher up you go. Makes sense, right? And then it also changes with changing weather. So, weather is controlled by the air pressure and the air movement and the water movement. So the air in a high pressure area compresses and warms as it goes down, and the warming gets in the way of cloud formation, so it's normally sunny in high pressure areas. Pretty basic, right? You might see some haze or some fog, depending on how much water vapor is in the air, and then low pressure is the opposite of that. So high pressure places is warm, is sunny, is compressed, not a lot of rain. Low pressure is the opposite. Okay, so high pressure pushes down, air descends, flowing out clockwise on the ground. Low pressure goes up, air flowing counterclockwise, rises and cools. And this is what forms the clouds and precipitation. So sunny over here, rainy over here. So make sure you guys can summarize this. Oh, holy cow, seriously? Okay. The humidity of an area is the amount of water vapor in the air compared with the potential amount that could be in there at the current temperature. So it's expressed as a percentage, depends on the air temperature, the pressure, and the water availability. So in Texas we have very high humidity because the temperature is normally higher, there's plenty of water relatively close to the equator, so on and so forth. So we have on Earth right now about 326 million cubic miles of water. 3,100 of this water is in the air as water vapor, clouds or precipitation. Okay. So again, you're summarizing, looking at the at weather patterns. The cooled air, the liquid's going to win. The warm air, the water vapor is going to win, and it's going to be sunny, cloudy, average. Cloud cover is moisture in the atmosphere, so water vapor that's gone one step further and formed the clouds. Covers about 40% of the Earth at any given time. If we didn't have clouds, we'd have a much warmer planet. Clouds provide a very important function in controlling our weather and the annual global temperature. Clouds also reflect sunlight back into space, and that's known as the albedo effect. So that's also a word that you guys should be comfortable with. Clouds reduce the amount of heat by absorbing the heat radiation and re-radiating it back down. So some of it they reflect back, and some of it they essentially trap down close to the surface of the Earth. Precipitation is any kind of liquid water. Well, any kind of water. So rain, freezing rain, sleet, snow, or hail. So it doesn't necessarily have to be liquid or solid water, I guess. And it's looking at the density, looking at the size, to look at the different types of precipitation. Okay, winds. A horizontal wind moves from areas of high to low pressure. Vertical wind, low to high pressure. The speed is determined by pressure differences, and then that Coriolis effect is spiral pressure, right? High pressure to low pressure zones. It's detected by an anemometer and direction by a weather vane. The direction is based on where the wind is coming from. So a wind from the east is an easterly. The Beaufort wind speed scale just gives us a range for the to kind of compare for people. So looking at like hurricanes and stuff like that. We've seen this already, looking at the prevailing winds and their directions. Okay, so warm front is warm air moves in, warm air from cooler air rises over the cool air mass and develops clouds and light precipitation. A cold front is cold air advancing into warm, and it pushes under the warm air. So that's what's bringing the vertical movement strong and thunderstorm, rain, stuff like that. A stationary front, it doesn't move, makes sense. Due to winds running parallel to each other, kind of gets it stuck in one place. And then occluded is where the cold front overtakes a warm front in the specific location. So, thunderstorms occur tropical, subtropical, temperate, and kind of subpolar, but they don't really occur north of that because you don't have as much precipitation, right? Any of the following precipitation with strong winds, lightning, thunder, moist air is going to rise because the frontal zone is lifting, and that's going to reduce the heat, which will lead to clouds with updrafts, and then you hit that window, that 42,000 feet, and it goes back down, and that's when it starts raining. So it lasts about an hour. Severe thunderstorms occur when the cold front approaches a warm front, and that warm front gives them more moisture and energy to the cold front, and so it has more precipitation. And so this is just a picture of what that looks like, essentially. Tornadoes are moving masses of air in a circle. Water spouts is when tornadoes happen over water. The center is very low pressure, which causes buildings to actually implode. The destruction tends to be very specific, a very small area right where the tornado touched down. Tornado Alley is Texas to Indiana, in that central Midwest area, and that's where where that air mass tends to hit in the right location. Hurricanes are actually the most property damage and loss of life. High wind speeds, high precipitation. They start over the tropics in warm ocean water, and then you get a lot of warm solar insulation, right? Warm water provides lots and lots of energy, huge evaporation with a lot of cloud formation and lifting up into the atmosphere, and then it drives it up into continents. So there's stages to a hurricane. As they move from how they form into when they're all done, you go from a tropical depression to a tropical storm, and then into the hurricane of different sizes. The eye is the center, and again, very high rainfall. Okay, and these are just some really cool pictures of different cloud formation, thunderstorm formation. You can see the fronts moving through and really see very clearly the difference of how the wind is pushing around the cloud formation. Okay, so El Nino is a part of the Coriolis effect, kind of. They're related. So an El Nino is something that happens every few years. You may have heard people saying, oh, this is an El Nino or a La Nina year. And what happens is the prevailing westerly winds are going to weaken or decrease or just stop altogether. And then that means that the surface waters get a little warmer. And so you bring more upwelling up. I'm sorry, you decrease the upwelling because there's no density change there. And then that leads to declines in fish populations. So it's just kind of the pattern every few years of more unusual weather that again messes, because that upwelling is so important, messes with the food chain. So weather is what's happening like right now or for the next few days, and climate's the average long-term weather of an area. So it's seasonal variations. The weather extremes are averaged over a long period of time. You're looking, again, just like when we were talking about the biomes, you're looking at the temperature and the precipitation. Those are the two main factors that are going to control our climate.